So far we've been looking at dynamical systems where they behave exactly as we expect. We have a delta formula and then that determines the new value, but we all know life isn't really like that. So we're going to talk about ways in which we see noise in the system. One first distinction is the noise additive or multiplicative? In additive, you just take the actual value, add some random value to it, and that gives you some new value. And the amount of noise doesn't really depend on how big your actual values are. So if a stock price is like $100 right now and it might fluctuate plus or minus $2, if that goes up to $300, is it still going to fluctuate plus or minus $2? That's what the additive noise model says. So the kind of absolute size of the noise stays the same even if the actual values are bigger. But the percent size gets smaller because the denominator in the percent is getting bigger when the values are bigger. Multiplicative noise would say, well, the noise is like usually plus or minus maybe 2 or 3%. And so if the noise is negative 3% this time, then the resulting value is 97% of the actual value. So the percent size is the same no matter how big the actual values are. But the absolute size is going to get bigger when that actual value is bigger. So let's go take a look at this. So here I have it set up. So that's additive versus multiplicative noise. Another important distinction is process noise versus observation noise. In observation noise, we're saying, well, our measurements aren't perfect. They've got a little bit of error to them. But my measurement on today's value doesn't tell me, doesn't affect my measurement on tomorrow's value, and it doesn't affect what the system does. But in process noise, that's saying that the system itself is behaving randomly, even if we can measure it precisely. And both of those can happen in the real world, but it's good to be able to think about one versus the other. These are related to Kalman filters. I'm not sure how you pronounce that. But they're a big thing in a lot of applied math. So now let's go take a look. So here's an observation noise model. I have my current value, and this might be my bank balance, which I would hope would have no observation noise to it. Or it might be a population that we're trying to count. You can imagine there'd be some imperfection in how we count a population. So I combine those two to get my first observation. And then the system does its thing. We have a delta amount and the new value, and then I get an imperfect observation of that value, and then it happens again, etc. So in observation noise, this is what's really going on, but all we can really see is that. All we really see is the observations. So I've got a sheet here where we just have a 5% compound interest kind of growth. I'm starting at 100, so my delta value is 5, so my next value is 105, same thing we've been doing before, but now I'm adding some noise to it and only plotting the value with the noise. So here I'm saying take this uniform 0, 1, convert it to a normal, standard normal, multiply it by something to make it bigger or smaller. Here I'm going to end up with a standard deviation of about 20. And then my observed value is the actual value plus the additive noise. But then this cell doesn't get used here or here or here. So whether this cell is high or low doesn't affect the next values of the process. So that's observation noise, and you can see how it tends to behave here. Notice the wiggling over here where the y values are large, like 700, is about the same as the wiggling over here where the y values are small, like 100. So that's additive noise, additive observation noise. We can look at multiplicative observation noise. The same thing is happening with the process itself. Starts at 100, has a delta of 5, then goes up to 105. And the noise, again, we're just taking this random, turning it into a standard normal. But now we're multiplying it by 20%, and then the observed value is the ordinary value plus 1 times 1 plus the multiplicative noise operating as a decimal. So here, if we get new random numbers repeatedly, can you see that the amount of change over here when the y values are large is quite a bit more in terms of like from 600 up to 700, that's a plus or minus of 100, whereas down here it's only a plus or minus of about 20. So that's multiplicative noise. You might say, oh, it's probably harder to count a population of 700 million people and be within 20 million people than it is to count a population of 100 million people and be within 20 million people. So that's additive versus multiplicative noise for observation noise. Let's talk about process noise. Here I don't have the randomness in adding to the observations, but I have randomness adding to the change amount from one time step to the next. Now typically we don't get to see the process noise either. And let's go look at what this looks like in a spreadsheet. So here we have process noise but no observation noise. I'm starting at 100. My delta is the same formula as usual, 5% times 100. That's my no noise delta. And then I have some additive noise, and that gets added to the no noise delta to give me a delta that isn't quite what we would have predicted. And then that's what I'm using to update my system. So if this number is large, this number is large, and then all the rest of the numbers will tend to be larger. And here I have observed values, and they're just equal to the actual process value, so I don't have any observation noise. So look how this behaves compared to how the observation noise models behaved. You actually saw there was an example where it actually went negative, and once it was negative, 5% growth on a negative value. Oh, here it went negative and just happened to come back positive. But once it goes negative, 5% on a negative value is negative again, and so it can run away to minus infinity. So all kinds of interesting things can happen when you have process noise. In the real world, we have both process noise and observation noise. So it's the same diagram as before, but with both aspects. And then in the even more fun real world, not only are we watching the system as it goes along, we're taking our observations and maybe tweaking the system, maybe pressing down on the gas pedal harder, or supplying a little bit more electricity to a heater, or adding a little bit more insulin to the bloodstream to try to control blood sugar. So we're making decisions based on the observations which have noise in them, trying to affect the system to keep it under control. So this is related to Kalman filters, which were first used to help Apollo navigate to the moon. These days they're being used in autonomous vehicles and rocketry, probably. They're used in healthcare in all kinds of ways. They're related to hidden Markov models, which we talk a little bit about in math319W. And in deep learning, they're related to recurrent neural networks, which are used to do speech recognition and text processing and stuff.